Welcome to video number 20, Econometric Subpractical Approach using STATA and R. Today I am going to discuss nonlinear regression functions. This is chapter 8 from Stock and Watson. If you'll follow chapter 8, if you'll read chapter 8 along with this video, you'll learn a lot. So everything same, but now you have nonlinearity in terms of variables. I am not talking about nonlinearity in terms of parameters. So we'll see that how does interpretation of nonlinear function is different than linear regression function. So here estimation method, statistical inference is almost the same as in linear regression functions, but coefficient interpretation is different. So look here, there seems a linear relationship between x and y, class size and test score. But in this case you have a linear model, but this linear model does not seem a good fit because you have this does not seem a good fit because it seems that model seems non-linear like this one. Okay, model seems a non-linear fit like this one. So what's the difference between linear and non-linear? In general, your standard interpretation is not valid, that one unit change in x leads to so many unit change in y. Now your interpretation will be different for this range of x in test score and for this range of x in test score. That's we are going to see that. So effect on y of a change in x depends on the value of x, that it's not constant. As in linear model we say that if x changes by 2 units, y changes by certain beta 1. But in this case it's not fixed, it's different from one range of x to another range of x, though change in x is the same in both the ranges. No, the assumptions are same, that u and x are independent, means they are basically there is the covariance between x and u is 0, x, y, IID. Big outliers are not allowed. You can watch my previous videos. No perfect multicollinearity, moderate level of multicollinearity must be there. And if you have single variable, so it's x square, x cube, it's a polynomial in x. You have more than one variable, you may have interaction of two variables, gender and education plus gender education interaction variable, price and gasoline consumption, to price into gasoline consumption, that interaction variable can be there. So all these are non-linear in variables. And if you have single x and you are taking its powers, that's called polynomial regression. Usually in economics we don't need polynomial more than 3 degree, so we know we don't need to go beyond that. So look here, you have a model where test score is a function of income, so that's one option, that linear model. Another option, quadratic model. Another option, cubic model. So whether a linear is a good fit, quadratic is a good fit, cubic is a good fit, so you will see the comparison between the three. So you may proceed like this, that you have created average income square variable and you have used it and it seems to be significant. So it means a significant variable from linear model has been ignored if you fit a linear model. So therefore quadratic seems a better fit over linear one. So here you see this is your quadratic fit, this is your linear fit, and quadratic apparently seems better fit than a linear model, and at the same time it has the coefficient of income square is significant. Let's move how to interpret. That's very important. That's why I have been talking about this video. You have income square here. Now this variable is basically making a difference in interpretation. Previously we were saying that if your income from 5 to 6, 25 to 26, 35 to 36, your change in test score was only 3.85. But now this term is making all the difference, because this will be 6 square minus 5 square. That will be different than 26 square minus 25 square, though difference between both is $1,000. So 6 square, 6 square, 5 square. Similarly, here you will have 26 square, 25 5 square. So this square term is making all the difference. So you see difference in test score in this range is 3.5, though change is only $1,000 per capita. Here change is $1,000 per capita, but change in test score is not the same. Change is $1,000 per capita, but test score change is 0. So that's how you interpret nonlinear model in variables. Its interpretation is different from one range to another. That's the main difference. And here in the last line you see caution. We don't have data $65,000, $66,000 per capita in. So therefore never talk about something which is not part of your data, or those values are beyond your data range. So you have a cubic model. Cubic model also have very significant coefficient. So therefore there is a close match between quadratic and cubic. Linear is rejected in this case. Now whether you want to retain cubic, whether you want to retain quadratic, the one way is statistically cubic seems better, but other way is common sense. You can decide at your own. So what we are saying, that our linear model is a fit versus H0 is linear versus alternative linear, quadratic or cubic. So we see when we apply the F test for coefficient restrictions, we fail to reject that income square and income cube coefficient equal to 0. So therefore we prefer cubic or quadratic model over linear model. So this is the summary, you can see it, and we'll discuss in next video about log, log, linear log, log linear, their interpretation, interaction variables, why do we need interaction variables, and some other concepts related to regression function, which is non-linear in variables, not non-linear in parameters for the time being. Thank you for watching. Take care.